Once you get far enough.
Okay, Danielle, what did you guys agree on? In the atmosphere, and Lauren, what did you and Dizang agree to? Atmosphere, and Tessa, what did you three agree to? Atmosphere, and Robbie, what did you and Elizabeth agree to?
Moon distance away.
Moon distance away, and Leia, what did you four agree to? Moon's distance away. So gravitational potential energy is energy that we're storing by placing a mass in a gravitational field, right? And last year we did, we did calculate gravitational potential energies last year, right? We used GPE. I think we said it was MGH. That is absolutely not how we're going to do it this year. In fact, we've never calculated a gravitational potential energy so far this year. We calculated some changes in gravitational potential energy and said that that was mg delta h. But this is not good enough for us this year. And last year we did have some issues with not always agreeing on the height. I mean, it was kind of arbitrary. We chose some reference level to call a height of 0. That was very arbitrary. Maybe we used the desktop, maybe the floor, maybe the ground level, which is lower than the floor. So we want to have something that's absolute this year, not arbitrary. But I think to answer this, we can use our simplified way of looking at gravitational potential energy. And right, if here's the Earth, we essentially are measuring height. Well, I guess we're typically measuring height from like the surface of the Earth. So if we're in the atmosphere, right, we're some height. If we're out a moon distance away, I mean, it would probably be up on the ceiling. But that's a much larger height. So we certainly have more gravitational potential energy a moon distance away than we do at the atmosphere. And I think that, and I'll get the questions in a sec, but I think the better way to think about this is we're storing energy by placing the thing in the gravitational field. And if we let nature do its thing, that gravitational potential energy is going to change into kinetic energy. If we don't have other friction. So we can definitely have more kinetic energy if we fall from up here than if we fall from up here. So that's actually a pretty healthy way to think about it. Robbie?
I mean, I agree with that, but like, does the height increase faster than the acceleration due to gravity?
Does the height up? Yeah, well, acceleration due to gravity does decrease, that's fine. And that's another great reason why we can't actually use
right,
this.
That's fine.
Acceleration due to gravity comes from our law of universal gravitation, right? And we can get acceleration due to gravity from this if we just divide it by the UFO's mass. So yeah, the acceleration due to gravity decreases with the distance squared, whereas the potential energy increases with distance. But it doesn't matter. I mean, it doesn't matter. Still, as this UFO is falling towards the Earth, if that's what it does, by the time it gets here, it's going to have the same acceleration due to gravity that something that we place there. So it kind of doesn't matter. But you're right. This would not be a linear sequence of changes. Go ahead.
Would it be healthy then to think that gravitational potential energy equals the mass times just like the acceleration, just like not g, but like whatever acceleration value would be?
Well, the healthier way is to not use that at all and to use this. And that's exactly what we're now where we should be 20 minutes from now. But gravitational potential energy, all right, is, let's see, so it's mass and it's this and it's that. Yeah, no, let's not jump ahead, but it's essentially Nick, are you good?
No, I'm good.
All right. So today, in our last 20 minutes, gravitational potential energy is kind of the starting point for topic 9.2, but there's actually some other variables that we need to care about a little bit more. So we have a related variable called gravitational potential, and then we also want to go back to our concept of gravitational field. It just dawned on me that this is exactly what I did this morning with my 10th graders, but not with gravity. A classic. Exactly what I did with my 10th graders on Wednesday. where we introduced electric potential energy, and then went on to say that, well, really it's electric potential that we care about a little bit more than electric potential energy. And then what's the next one? What's the thing that we really care about?
Difference.
Electric potential difference. So we have all those same concepts with gravitational fields as well. What's that?
Is there gravitational potential difference?
You know what? Typically not, because we typically don't allow things to have a large change in gravitational potential. I mean, we are essentially at a uniform, we live on a uniform gravitational field, right? We live at the surface of the Earth. Yeah, we can go to Colorado and change by like 1%, not even 1%, 0.1% difference in the gravitational field strength. No. We don't live in a world where it makes sense to talk about gravitational potential differences, or meters per second squared inch, if you want to try and have a synonymous, like, bad word for that quantity, like voltage. So anyway, the objectives that we're starting today, and we'll certainly continue with on Tuesday, we have some definitions, right? We want to define gravitational potential and gravitational potential energy. We want to state and apply the expression for gravitational potential due to a point mass. We want to state and apply the formula relating gravitational field strength to something called gravitational potential gradient. I guess that would be Robbie's gravitational, it's similar to his gravitational potential difference. We want to determine the potential due to 1 or 2 point masses, not 3. And we want to solve problems involving gravitational potential energy and gravitational potential. So we have a little bit of catching up to do with the notes because we got ahead of ourselves a little bit in talking about the UFO. But in this course, we do not say that gravitational potential energy is equal to mgh. There's just too open to interpretation with what we do with that h. And the g is not always the easiest thing to do in the world either. We haven't, as again we said a few minutes ago, we haven't defined gravitational potential energy yet. However, back in topic 2, so a long time ago, we did use mg delta h, which is totally valid. Right? There's nothing wrong with using mg delta h. Wow. As long as we're at a place where the value of the gravitational field doesn't change too much, there's nothing wrong with that. So, definition, right? We wanted to define gravitational potential energy, and here it is. It is the work done in moving a mass from infinitely far away to wherever the heck we moved it to. It's how much work we have to do to take something that's located infinitely far away from the source of our gravitational field and move it to that spot. Right? And it kind of makes sense that work and energy, we know, are very related. So we don't have any problems with like different units or anything. Alright, so let's attempt to make a little bit more sense of that. As we already stumbled upon, it is a little bit difficult when we start covering large distances to know how much force we have to exert to move something. Right? This gravitational force, as I think Robbie pointed out, right, that does get smaller and smaller as we move further away from the source of our gravitational field. So, we know that work is force times displacement, at least if we're, if they're in the same direction. That force changes as we move. So here, this is just a graph of force on the y-axis, distance from, I guess if we're moving from, the Earth, this would be distance from the Earth. And it's not linear. It does, I suppose, follow an inversely proportional relationship. So infinitely far away, it actually shouldn't really take any force because the Earth is pulling so weakly on our thing if we're infinitely far away. So if we start at infinity, right, it doesn't take much force at all to move it. But then as we get closer and closer, we have to use more and more and more and more and more force until we get to the surface of the Earth. And the work that we do would actually be the area under that, although I've actually never seen a question posed that asked us to utilize the area under that in reference to gravitational force. All right, let me ask a question about this graph, and then I'll shut up for a minute and let you guys ask questions. I called the surface of the Earth here, and we can see that our inverse relationship kind of dives at that spot. And then we actually need less force again to keep moving beyond the surface of the Earth. So can you check in your foursomes and see if there's anybody that thinks they have some intelligent thoughts about why the maximum force to move that thing closer to the Earth occurs at the surface, and then why it actually decreases to zero as we keep going. Try to see if you're sitting near anybody that can make any sense of that.
So once you get inside that sphere, gravity decreases.
Yeah, gravity decreases.
Remember this from what?
Inside of the circle of gravity is strong. It's like somewhere.
How did you do that? What did you do?
No, it's.
How did you do? Why did you take it? Yes. Oh, okay. All right. Now you're not supposed to get pulled down. Okay. All right. It should be good. Yeah. Volunteers? Volunteers? All right, you heard from Robbie enough. All right. Shot cars pointing at cliff. All right. Go for it.
So
Nice and loud.
So as you go underground, the mass of the amount of mass of the Earth that's actually below you also decreases. It decreases a little bit.
All right, so we're taking something. I guess it could be our UFO. I don't think I have any UFOs. That's too big. Here's our UFO. So here's the surface of the Earth, and then we go underneath that. So say again what you said.
So originally when you're at the surface,
Yes.
all of the mass of the Earth is below you.
Pretty much. Some of it might be, that side, but pretty much.
Produces the gravitation field.
Okay.
And then as you go down, there's less of it. There's portion less of the
Okay.
mass of the Earth below you.
So there's less mass below you, but also there's now mass above you. Right? So when you're out here, pretty much the mass, every molecule of the Earth is, if you're far enough away, is pretty much pulling on you in the exact same direction. When you're at the surface of the Earth, that's largely true. It's not entirely true. You definitely have stuff pulling you that way. You have stuff pulling you that way. But still, most of it's over here. But Cliff's right. As we go beyond the surface of the Earth, we have less mass on this side of us, and we start having mass on this side, which is pulling that way. Right? So not only is it that there's just less pulling us this way, there's now actually pulling us the other way. So we don't have to pull as hard because, well, this stuff's not pulling us hard. But we have this stuff which is actually helping us out, right? Pulling it in the opposite. Is that true? Now I'm feeling like I'm saying something wrong. So that keeps being true, keeps being true, keeps being true. But then we get here. Yeah. Hi.
Oh, say like someone took a big drill, right?
Well, hold on.
Okay.
So now we're here. Now we're here. What's our weight?
Zero.
It should be zero. The net gravitational force should be zero if we're at the center, because we have just as much stuff pulling us this way as this way, just as much stuff pulling us that way as that way. So we should actually get, is that true weightlessness? That might. We would certainly have an apparent weightlessness here. And I'm having trouble admitting it, but we might actually have a real weightlessness right there. So Nick, go ahead. So we drill a hole all the way through. Right?
No, like say the hole you made before, right?
Yeah, right here.
say you drilled through at an angle, so like
Yeah.
you were parallel to the top, right?
Drill at an angle, so I have no idea what you're talking about.
Can I just draw it?
Yes.
Okay.
You cut that like.
Like if you took, say you drilled, somehow they drilled a shaft
Alright.
that way,
Yeah.
and somehow you got inside the shaft without just like falling that way. Would you be pulled downwards like this way, flatten that way if you got to like here, since all the mass is below just here?
Okay, so move out of the way. So you start here and you just kind of jump into this hole.
Yeah.
Did you reach the bottom?
Like,
Um,
do you see what I'm trying to say?
Well,
I
think so. I think so. So you're here, and I mean, so this is not straight down. It would almost be like you're crawling into a cave that doesn't quite go straight down. So yeah, I mean, So number one, I don't think you could jump, because you would just, well, you would jump, but then you would hit here. I mean, I don't know. Does that answer your question?
Yeah. But like, would you have a lot more gravity down here than up here that like flatten by it or something?
Would you have more gravity here? No. You have less.
No, I mean like once you get to the middle, would you be flattened by the force because all the mass is below you?
Force, the gravitation
Yeah.
force, like
Yeah.
the stuff pulling on you. Once you get here,
No, once you get like down the shaft. In the middle.
so we're on your shaft or on the new shaft that goes
My
straight?
shaft.
We're on your tunnel.
Yes.
And we're just hanging out right here.
Just jump.
No, we would have a smaller root and we would have at the surface because there's less stuff pulling us this way. There's there's a very large chunk of earth up here pulling us the other way. So it's not like it's not like we're getting pulled on by two ropes. Right? I mean, like these are field forces. So no, I think we'd be pulled on less. Now, what I thought Nick was going to ask at the beginning was, what if we drilled all the way through, like straight through the middle, and jumped into that? That's what I thought he was going to ask.
Oh, that's
He had to
another
ask
good
something weirder. I don't think so. Who said we get stuck in the center? I absolutely disagree. Absolutely disagree. Well, eventually, if we didn't evacuate it from the air out. This does not do a good job going through the center, so excuse me for that. So we jump, all right? We accelerate. We don't accelerate 9.81 for very long because it pulls on us more weakly as we go down. And then we get here and describe my motion when I get there.
Still
Fast. Really fast. My acceleration when I get there will be 0. But I had an acceleration that started at 9.81 and slowly decreased to 0. But in the entire direction, the entire time, I am cruising. Can I figure that out? 3,000 miles, I think, is the radius of the Earth, roughly. I can't figure it out. So I'm on thousands of miles per hour if we ignore air resistance. So I keep going. And I start to lose my speed as I pass through. And how fast am I going when I get here if we ignore air resistance? 0. Because whatever speed the Earth gave me as I fell this way, it takes back once it starts pulling on me in the other direction. Completely analogous to throwing something up. That whatever speed it lost on the way up, it gains on the way down. More complicated, because we don't actually have a differential acceleration, but very analogous to throwing something straight up. So I get here, I go to 0, then I come back here, cruising again, 0, I'd be oscillating back and forth. Because of air resistance, it would be damped, right? Because of air resistance, it would be damped, but it's going to take a long time, a very long time, before I'm stuck at the center. Well, if I had air resistance, yeah. But it's still not going to be critical damping, for sure. So I'm still going to pass through. But you're probably right. I'm probably not going to go too far through. No, probably not. You're right. I forgot about terminal velocity. Alright, so anyway, you know what? That was even though that was a discussion worth having. Alright? So back to where we started. as we move something from infinity to the Earth, the force changes, I guess was our. Yeah.
Is it a good idea to think of that graph as having a horizontal axis to it?
Oh, I think it would. And I'm a little upset with it that it doesn't look like it does. Yeah, I'm a little upset with it that it doesn't look like that's the case. Alright. So let's knock one objective off. This is a quick one, and then I want to get to something that should start to allow us to quantify this gravitational potential energy and understand gravitational potential as well. What's this?
Solar
Maybe
system.
I should turn the lights on. It's not the solar system. That is the Earth in the middle, yes. We see blue and we actually see some green on there as well. That's the Earth. Satellites. Okay? So each white thing is a particular artificial satellite. So you can see that there's actually a lot in this one orbit right here. So these are all like the geosynchronous satellites that are always at the same spot in the sky above us. So they're at that perfect orbital radius where their circular velocity is exactly the same as the Earth's rotational velocity. So the satellite that gives me television would be one of the ones in this perfect orbit right here. We have lots of other ones as well. Now, if I wanted to move a satellite from, I don't know, this is going to be difficult because these are in 3D. If I want to move one of these geosynchronous satellites, let's pretend this is two-dimensional. I want to move it closer to the Earth. Let's not do that. Let's move it a little further away from the Earth. Let's actually take one of these ones and decide we don't want it there. We need some extra satellite television service, so we move one of these inner satellites out to here. Do I have to do work if I'm going to move it further away from the Earth? Yes, I do. If the Earth is pulling on it this way, right? If I want to move it the other way, I need to push pretty hard to move it further away from the Earth. Just like I need to push to get this dry erase marker further away from the Earth. So yes, I have to do work. Good. And what about if I moved it? Yeah, I don't actually know what I want to ask. But what I want to say is that the route that we take does not play a role in how much work I get. So if I go from straight point A to point B, that requires the same amount of work as if I started at A, right, moved over to C, maybe moved further away to D, moved over on the other side to E, and then back to B, right? That would be the same amount of total work that I do. Sometimes there would be negative work as it's moving closer. The amount of work done as we move something around within a gravitational field is independent of the path that we take. All that matters if we want to calculate net work would be the starting point and the end of it. All right, I don't want to pause for questions because there's just one other big thing that I want to say. So potential energy, well, we said the definition of the gravitational potential energy was the work done in moving something from infinity to its spot. At infinity, we're going to go ahead and set the potential energy equal to 0. It's got to be 0 somewhere, right? That's one place we could put it. No gravitational potential energy when we're infinitely far away from the Earth. That comes with a major repercussion for all other gravitational potential energies. Anybody see it? Major, weird ramification of assigning a potential energy of 0 to being infinitely far from the source of the field. Jeffrey.
It'll increase as the distance decreases for a bit after infinity.
What do you mean?
Because it'll go to 0, and then when you're no longer at infinity, it'll be non-zero. It'll increase.
Well, we can't go further than infinity.
No, when you get closer.
So we start at infinity and get closer?
Yeah.
And what increases? Potential energy?
The potential energy would increase
Ooh, I
from
think
0.
not. I think not. Because that would be like, all right, the ceiling is pretty far away from the Earth, the ceiling lights are pretty far away from the Earth. If they get closer, their potential energy doesn't increase, right? It decreases. So what's the ramification? Oh no, that's a technicality, that's not a ramification. Emily?
Would it stop, like, I don't know, would it stop increasing as you got farther away and start decreasing again?
No, we can't get further away than infinity.
No, I don't mean that. I mean just at a point.
No, it won't. Alright, UFO had more potential energy where? In the atmosphere or the moon distance away? Moon distance away, right. Would it have more or less potential energy a moon distance away? I'm sorry. We're at the moon distance away, we bring it, I don't know, Jupiter distance away. Where does it have more potential energy? Jupiter, right? Because it's further away from the Earth. And more potential energy due to the Earth, right? It would have Jupiter potential energy. We take it outside the solar system, more potential energy or less potential energy? More. We take it to infinity, more potential energy or less potential energy?
Less.
More! How less? We're further away.
But it said
But
zero.
why is it
before.
0?
The potential energy is zero, infinitely far away. So Elizabeth, what does that mean about all other potential energies? They are negative. Okay? So every gravitational potential energy that we ever deal with will have a negative value with the exception of if we're infinitely far away. And it's zero. Okay? A little bit weird, but it's got to be zero somewhere. And we could never agree last year about where the potential energy is zero. Now we have to agree. Because everybody in the world is saying, yep, we're going to have zero potential energy when we're infinitely far away, but we have less than zero everywhere else. Alright? So all gravitational potential energy values are zero or negative. We never have a positive amount of gravitational potential energy. That is actually a great ending place, because that should sink in a little bit before we get this done. Alright, we can pack up, yep, come.
Did they do that? Oh, I was just gonna ask. Did they do that because there's no absolute, like, greatest positive energy?
Well, that's true.